And we'll do a longer session sometime when I can be home. Okay, so share the screen with you guys. And you can just keep busy until iftar. At least only. Since there's a recording, you can watch it later as well, right? Okay, so unfortunately, I've been reading your exams. I'm not finished yet, but I'll be finished probably tonight or tomorrow. They're pretty bad. You may have realized this. The grades are very, very bad. Maybe you didn't expect it. So we'll have a discussion about the exam later in class. One thing I can do is just quickly go over the solutions to the exam questions so you guys know what the solutions are. Yeah, and then we'll talk about the exam later as well. So it was a midterm. Okay, quickly going over the midterm. This question, a few people got this wrong, but most of you actually got this one right, both sections. So I'm not going to focus on this too much. But I'll hand out the answers anyway later on, so you can see that one. This surprised me. A lot of people got this wrong. First thing you got wrong is that if they're in series, you're going to convolve them, right? And if they're in parallel, you add them. I talked about this in class, but I think people just got it wrong. So if it's this kind of system, then the answer is going to be the convolution of the two. And if it's the other kind of system, it's going to be adding. So what I'll do is just quickly snip this. The other thing I'm thinking is in the remainder of the class, just to make sure you guys learn more of the material, I want to do the whole flipped class thing, where what I'll do is I'll put a video up about the topic, and I'll give you the page numbers from the book, or just like the section of the book or topic for next week. So for next week, I want to do, should we do first order response for systems of filters? Okay, so next week we'll talk about, we might start this right now, but filters and systems described by differential equations and first order systems, right? So read up the section on filters, particularly first order filters in your book, and we'll analyze these filters and kind of analyze systems. I kind of did an example of this before the exam, but I think I didn't ask it on the exam because I thought it would be too complicated, and I just did that one example. But read this up, and in class next week, what we'll do is examples of that. And I think for the remainder of the weeks, and also maybe we should start the Laplace transform. Okay, so 1 hour I'll do examples on this system analysis, and the next hour we'll do examples of the Laplace transform. And I want you to arrive in class with print out this slide if you can, this final slide with the transform pairs, and bring a pencil and bring a paper. So I'm going to ask you all to just do questions. We're just going to do questions in class, okay? And I'm going to put up a video or two with explaining the Laplace transform and so on. Not my videos, other people's videos. And hopefully you'll understand it. What you don't understand when we're doing it, you'll figure it out, okay? So yeah, so that's how we'll go right now, because I think that's just an easier way for you guys to get ready for the finals. So anyway, so if you have these two systems, the answer was that the response of the composite system is the convolution of the two. There's multiple ways to do the convolution, and any way is fine, but it has to work, right? Some of you tried it different ways and couldn't do it. I tend to do it, let's see, if H2 only has these three terms, right? I can just write down the convolution. First of all, there's this is H2 of n. I think I did it a different way on the solution sheet, so you'll see the solution sheet as well. I'm sorry, this is all stuck in green. Plus 8 delta of n minus 1 plus 6 delta of n minus 2, right? So now the composite, which is H1 of n convolved with H2 of n. Sometimes you write it like this, just a parenthesis to show it's the convolution of the two. So you have this thing multiplied by 2, first of all. So we have H1 of n times 2. Plus you'll add 8 times H1 of n minus 1 plus 6 times H1 of n minus 2. Okay, So this is equal to 2 times 2 delta of n. So what is h1 of n? 2 delta of n, 0 delta of n minus 1, plus 6 delta of n minus 2, plus 2 delta of n minus 3, right? So we put those up. 4 delta of n plus 12 delta n minus 2 plus 4 delta n minus 3, right? And then we have 8 times h1 of n minus 1. So that means every time you see n, you replace with n minus 1. So this is 2 delta, oh, sorry, multiplied by 8, right? 16. Plus 8 times 6 is 48. Uh, 6 times 6 is 36. No, so I see a minus 2, right? A minus 4. What did I do wrong? I did this wrong? I did. Should be 16 here. As you can see, I'm kind of unable to talk anyway. So plus have delta of n minus 3. So this thing is going to be delayed again by 2, right? So we got I multiplied by 6. So we got 12 delta of n minus 2 plus 36 delta of n minus 4 plus 12 delta of n minus 5. Okay. So you add those, you got 4 delta of n minus 1. Oh, sorry, no, delta of n. Plus 16 delta n minus 1 plus 24 delta n minus 2 plus 52 delta of n minus 3. And then you add 16 and 36 and get 52 delta of n minus 4 plus 12 delta of n minus 5. Now, this is the long way to do this, but there's kind of a shortcut to doing this. When you're writing it down, you write like delta of n minus 1. Or you can just write, like, instead of delta of n, write n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. And then when you do these multiplications, like this one, you have 2 of this thing, right? 2 multiplied by these delays. So you got, here you got 4, 12, because this is at n minus 2. And then this thing multiplied by 2 is 4. And then you have this whole, like, because these are the coefficients, it's like 2, 0, 12, 4, right? Those are, I mean, like 2, 0, 6, 4. So those are the coefficients. I'm so sorry. I'll be back in a second. As you can see, I've got a bad case of the flu. Okay, so, and then you delay this by, let's see, which one? Okay, delayed by 1 and multiply by 8 instead of by 2. So if I multiply these coefficients by 8 and delay by 1, that's like 16, and then 0, and then 48, and 16. And then the next thing says multiply by 6 and delay by 2. So you start here and multiply by 6, so it's 12. That can't be right. And 24, yeah. 12, 0. Okay, that's right. 36, and then 12. Okay. and then you add them. You're actually doing the exact same operation I did up here. So this is method 2. Except like it looks a lot neater like this, right? So if you add them up, you'll get the same coefficients, 24, 52, 52, 12. And you can kind of interpret this as H1 convolved with H2 is equal to of n. Did I just do? Okay. Delta of n plus 16 delta of n minus 1 plus 24 delta of n minus 2 plus 52 delta of n minus 3 plus 52 delta of n minus 4 plus 12 delta of n minus 5, which is the same thing you found with the previous method, and this is kind of easier to do. Okay, next one. What was the example? Okay, next question was for the following function, find the amplitude. So we've been talking about amplitude, phase, frequency nonstop. So I kind of thought you guys had the definitions for this. I don't know if I even did this in class, that's the thing. But I talk about a lot of these concepts. We've calculated frequency. I kind of assumed you guys would know. But a lot of people got this wrong as well. So let's do this one. Okay, to find the amplitude is not just the height total. This height, if you call it, is 2 times the amplitude, okay? And you can see, like I've accepted any number which is close to 1, because this is -1, this is 0.998, and for part A, I would say the amplitude is approximately 1. The period is the time it takes to go, and a lot of people got this one correct, but some people got this wrong as well. Time it goes from one point to another point, right? The peak to peak, time for repeat. And so this is, if you subtract from 0.007508, 0.003534, that's your period. Okay, and if you want to calculate C, I won't do this. I'm going to get out the solutions. It's in the solutions. 1 over T, which T you calculate in part B, right? That's the frequency. And the phase, so a lot of people couldn't do this one. The phase, to find the phase, you have to decide if it's a cosine or a sine, right? Cosine, so you have A cosine 2 pi f t plus theta, okay? And this is not t, because of the way this is defined, this thing is x is equal to y. I didn't take any points for writing t here, because I do this all the time, but yeah, the variable here are x and y. The variables are x and y, right? And so yeah, is equal to y. So your A is approximately 1, and you just pick one of these points. Like I can pick this first point or the second point, whichever one you want to do. And you write cosine, in fact, you can just use this one, 0. So this is the amplitude, right? And x and y points here. So, and A, I'm going to assume it's just 1, right? So 1 times cosine 2 pi times this f that I found. Okay, so let me kind of calculate t. It's 4, 7, oh dear, 10, okay, times 0. Yeah, times 0.003974 times x plus theta, where x, you can put any x. So like I said, I can use this x, right, is equal to y. You can use any one of these. For x, you can put the number 0.003534, and for y, you can put 0.9998. And then all you need to do is solve this equation, which is a simple equation. So like your theta is going to be inverse cosine of 0.9998, since you take the inverse cosine of both sides, minus 2 pi times 0.00. Oh, I'm sorry, this the frequency is 1 divided by 0. Okay, times the frequency, which is 1 over 0.003974, multiplied by 0.003534. Okay, so if you calculate this, you calculate the phase. And for the equation, I was expecting to basically write this, right? Y is equal to cosine. I don't know what this angle is, whatever this turns out to be. But anyway, 2 pi times x, let's say, divided by 0.003974 plus theta. Okay, so that's the actual equation for this line, for this cosine. Okay. Next question. Okay, this was just a convolution question. Again, this continuous time convolution. Now, we did this, I think, several times. So, surprising number of people got it wrong. I'm not sure if we should do it again because it's just we did it several times in class. But this is a recording, so I'll do it in case you guys can look it up later. Okay, so this is the equation. Okay, so what we said was the convolution equation, and I do give partial points, so at least try to do what you can, but it has to actually be correct, like at least more or less correct. I would prefer that it be more or less correct. So yeah, h of t minus I don't like doing one person did it this way, which it will work, but it's then they got the math wrong, right? Okay, I'll do it this way because this is the more complicated one, and I've already done it the other way several times, and it will be in the solutions as well. So anyway, let's do it like this, because the other method, when I say the other way, which is easier, to put h of t minus tau, x of tau d tau. Both of these will give the same answer. So anyway, minus infinity to infinity was x of tau, it's u of tau, and h of t minus tau. Let me make this big. If you're watching on a phone, that's going to be hard. Okay, so h of t minus tau then is 7 e to the minus 3 times t minus tau, u of t minus tau d tau, which is equal to the integral from this is like, remember with t minus tau, I actually had you guys plot something like, right? So that, remember, was like this. It would actually be 1 until you got to 3, and it was 0 after that. So it's the other way around for a u function, right? So the integral is going to be from, and then this thing starts at 0. So, and they both have to be equal to 1. Right, for this integral to exist, because wherever they're both 0, wherever either one of them is 0, if this one is 0 or this one is 0, then the product of these two will be 0. And the only way you can have a non-zero integral here is with the requirement that your t is bigger than 0. If your t is less than 0, then this u function will end early here, and then there'll be no overlap region where both of them can be positive, right? So anyway, so the integral is from 0, because this u of t starts at 0, until the time t, because u of t minus tau, we change actually the t minus tau, right? So this is t, the x-axis is tau, this is u of tau, right? So integral from 0 to tau of 7 e to the minus 3 t minus tau d tau. So whoever did this, they accurately actually figured out that you need to take out the e to the minus 3t out, and then you have integral from 0 to t of e to the 3 tau d tau. I think somewhere around here is where they got confused. 7 e to the minus 3t, and then you have e to the 3 tau divided by 3, and the limits are t and 0. And so this is equal to 7 e to the minus 3t multiplied by 7 over 3, because I'll take the 1 over 3 out, e to the 3t minus e to the 0. And remember, e to the 0 is 1. But then you multiply this out, so you're going to get sorry, 1 minus e to the minus 3t, okay, which is the answer. So this is kind of a longer method. It would be a lot easier if you just use this integral, just based on the fact that then this thing doesn't have to be t minus tau, then that gets to be just tau. And you don't have to do that last step, multiplying it. Okay, next question. This one. Okay. Okay, so this is the Fourier transform, and I asked you to use the table. So if you try to do the integral is extremely tricky. We actually did the integral in class, but you would have to really do, to do the integral easily, you need to actually, and this was like a continuous time Fourier transform as well, so that I think threw people off. A couple of people did the discrete time Fourier transform. A couple of people realized that this was periodic and tried to use the formula for the periodic Fourier transform, but for cosines, cosine is a very special function. Even though it's periodic, when you look at the Fourier transform, if you just looked at the right table, you just have the answer. So that's Fourier series. This is Fourier transform. So yeah, this is the one. Cosine is here. See, it's very special. Okay, so it's not like the regular Fourier transform, the regular periodic Fourier transforms. Other things like square waves and triangles and stuff, you do use this continuous thing. But for the cosine, okay, the reason that it doesn't work for the cosine is because the Fourier series coefficients for the cosine, I think you didn't calculate those correctly, because only one of those is 0. Okay, so I'll do that in a second. So I was expecting you to just look up the answer from this from here, from this line. Okay, and I'll stick that here. And the only difference between this and this is that omega 0 is equal to 300 pi t, right? So the answer is the Fourier transform of this. So let me put this way. The Fourier transform of this is equal to pi times delta of omega minus 300 pi plus delta of omega plus 300 pi. I'll do the next step. I'll do the next two and then kind of get back to A again, because a couple of you did something kind of weird with A. So anyway, so here instead of t, I have t minus 0.2. So I look up the part in the properties of the Fourier transform, where you're going to delay by time t. Okay, so this is a time shifting property you can see on that line here. Okay, so if t is replaced by t minus t0, right? What is your t0 here equal to? 0.2. That means you take the Fourier transform you found before and multiply by e to the minus j omega t. So this is equal to e to the minus j omega times 0.2. Okay, and then you just take this part, copy, paste. Okay, that's the answer to the second part. And the third one, you have multiplication in the time domain. Multiplication in the time domain means convolution in the, by the way, just I hate it when students write this, so always put the Fourier transform sign around the function. They're not equal to each other. It's the transform, right? Okay, so multiplication in the time domain gives you convolution in the frequency domain. Let me actually do this in the next page. I'll just okay, and let's take And so I need the Fourier transform of both these functions. So the first one I found the Fourier transform for already. It's the cosine, right? Actually, let me do this. Just want to do part C and copy it to the next page. Okay, so I have cosine, and the Fourier transform for this was pi times delta of omega minus 300 pi plus delta of omega plus 300 pi. And then the Fourier transform for the rectangle function is also on here, this part. Okay, so the Fourier transform here, now here you can see, right, t divided by 0.1, so our t is equal to 0.1, right? So this is equal to 0.1 times sinc of 0.1 omega divided by 2. That is our Fourier transform. And now we want to convolve these two functions. So the convolution, so the Fourier transform of this thing is equal to the Fourier transform of the first one convolved with the Fourier transform of the second one. So that tells us this is equal to the first thing here, write this, copy it, okay. Let's make this quicker, write this. This thing convolved with this part. Now when we do the convolution, the constants can go up here, okay? And now I have, and also when you do convolution, if you have the convolution of the sum of two functions with a third function, right, then you can actually convolve them separately and then add. Convolution distributes over addition, right? So we have minus 300 pi convolved with sinc function here, plus delta of omega plus 300 pi convolved with the sinc function, same design function right here. So when you do these convolutions with the delta function, this is like a very special property of the delta function. I think it might actually be on the formula sheet, I'm not sure. Maybe not. You could do it if you calculate the, yeah, I didn't put that on directly, but it kind of comes from this property. Look at this. This looks like almost like the convolution function, right? And you can see that whatever this delta is pointing to, which is the x, that's the value that comes out here. So whenever you convolve anything with a delta function, all that does is replace the variable here with the variable that's inside the delta function, okay? So it basically shifts the position of the function. So this is equal to, I'm kind of memorized this, but I will also show you why that's the case in a second. 1, 2, oh, didn't need to close that yet. Plus sinc of 0.05, and then again, omega here is going to be replaced by this whole omega. Okay, so omega plus 300 pi. Okay, and then I close this function. So this is the answer. Now, why did I say that this convolution is equal to this? So I'll just do more general. Any f of omega, if I'm convolving some function f of omega with the delta function omega minus omega 0. Integral omega to infinity of, usually use lambda. And just to make it easier here for myself, I'm going to write delta of lambda minus omega 0 times f of omega minus lambda. d lambda. Okay, so this is the convolution equation again. This may look really unfamiliar to you. If you think of this function as being a g of omega, it kind of makes sense. We'll go through it, and if you don't understand it, then let me know. Like, I'll try to make it work out. Okay, so this convolution, and if you look at this convolution and this formula right over here, you can see kind of this is the integral y. Also, like, you can, anytime you want, you can replace this delta of s. So I'll just kind of snip those two things from the formula sheet because those are useful. Based on these, first of all, just to make it look like this, I'd like to switch the places for omega 0 minus delta. So this is equal to integral minus infinity to infinity f of omega minus lambda times delta of omega 0 minus lambda, d lambda. Okay, that looks like this, x minus y, right? And what it does is it takes out this thing, but sets y equal to x inside it, right? So here I have this, so I'm going to set lambda equal to omega 0 inside this function f. So this is equal to f of omega minus omega 0. Okay, so in short, if you have any function f of omega and you convolve it with delta of omega minus omega 0, you will find f of omega minus omega 0. And if you have any function f of omega convolved with delta of omega plus omega 0, that will be equal to f of omega plus omega 0. So this convolution with the delta function moves your function around. Okay, next one. Oh, that was it. I was also going to talk about this using the other formula for cosine. A couple of you realized that this was a periodic function, and based on that, you use this last continuous time Fourier transform with periodic functions, this line. Now, the thing here is, okay, here we go. You can. Only thing is you have to get the right coefficient CK. So what are the coefficients CK? You could calculate this, or you could actually look it up. And if you went to the Fourier series to find the coefficient CK for the continuous time, I'm kind of worried some of you may have used the discrete time Fourier series coefficients. But continuous time Fourier series coefficients are here, right? So it's this one. Okay, so this is an infinite summation. However, all of these CK terms are 0 except for C1 and C minus 1. So from here, I'm getting 2 pi times 1/2 delta of omega minus 2 pi k over, wait a second, this is for continuous, this is for discrete time. Sorry. Can I write down the continuous time alternative for this? I didn't. Fourier transform pairs. Yeah. 2 pi k over n. This is a problem with this formula anyway. This is good that I found this. Guys, if you have a formula sheet, I think there's something wrong with this formula because this is for discrete time functions, not for continuous time functions. This should say omega 0. Somehow, as I was writing the formula sheet, I knew I'd make some mistake. This should be an omega 0. Okay, so anyway, so you've got k omega, it should say k omega 0. Sorry. where omega 0 is the frequency of the function. So it should be like, but the only ones that are non-zero, like I said, because of the coefficients, are omega 0 plus 1/2 delta of omega plus omega 0, which is minus omega 0. Okay, so for the -1 case. And of course, that also is equal to pi of delta of omega minus omega 0 plus delta of omega plus omega 0. Okay, so yeah. You should get the same thing from this equation. If this equation were correct, I will fix this. And on your own formula sheet, please fix it by yourself if you have one at home. Okay. All right, so that was that part. Next one. What are we going to do next? Let's look at some of these slides and see what we have in store. Okay, so the first part is first order systems. I still have some time. Now, magnitude phase representation of the Fourier transform, right? So you have magnitude and phase representation is when you look at the absolute value and the angle. And again, like I keep sort of hammering on about this, but complex numbers exist on the complex number plane with real numbers along the x-axis and imaginary numbers along the y-axis. If you pick a point, we generally use z to represent a point in imaginary space. This is x plus j times y. Unlike mathematicians, we use j to denote the square root of -1. Okay, and when you look at this, you can look at it in these Cartesian coordinates, where this coordinate is y and this coordinate is x. But you can also look at it in polar coordinates, where you have a radius r, right? And this r is equal to the magnitude of z. And it's the square root of x squared plus y squared. And the second thing you need in polar coordinates is this angle, which is theta, right? What's the angle theta? This is equal to the inverse tangent of y divided by x. You have to take the inverse tangent carefully, because depending on, you know, whether y is negative or positive, you can end up with different angles. If you ever take complex analysis, which is a more complicated thing, theta can take any value, and it's almost like it's not just a plane, but there's a whole bunch of planes, and they're spiraling up. Like imagine they're kind of like a, you know, those child lanterns that they have like squished together and then they spiral up. Yeah, that's how you imagine it in the complex plane being. Like it's actually kind of infinite layered. But yeah, but for this purpose, we usually assume that theta is just between the intervals minus pi and pi, or 0 to 2 pi, right? Okay, and if we know r and theta, this x plus j times y can also be written as r times e to the j theta. They're the same number, because what is e to the j theta equal to? Is r cosine theta plus j times r sine theta. Now, this whole e to the j thing is sounds very complicated, because exponential is just a normal function. But I have a couple of videos on the webpage. If you look at the resources, there's a channel called 3 Brown, 1 Blue. I love that channel because they have such nice animations, and they explain a lot of these, and they have actually a whole video about what this thing is and why it exists. But yeah, exponential functions are used in many different ways. In some of your courses, you might see e to the matrix A. There's actually a thing like that, where e to the A, where A is a matrix. So we don't get into that in this class. But if you ever do control theory, it might show up. Okay, so anyway, so we have e to the j theta, where this is the r cosine theta plus r sine theta, and that's exactly, you know, this is exactly the equation for x, and this is exactly the equation for y. Okay, so now we're looking at our signal and our system as having a phase in the component. I think I went through some of this at least 2 classes ago. So the magnitude is important. Another thing we look at a lot is this absolute value of x squared, which is called the energy density spectrum of x. Okay, so how much of each frequency shows up in x. You use this particularly when we're talking about random signals, because random signals, the phase is really difficult to deal with, but the magnitude can be very important. Like, is your signal a cosine or sine? Is it changing very quickly? Is it changing very slowly? So that's very important. And we'll look at that in filtering as well. And the angle, it doesn't affect the amplitude, but there's a website. Actually, I still haven't put it up on the webpage, but it's somewhere in my, yeah, there we go. Phase distortion. I'll just link this into the, sorry, I didn't manage to get rid of that. I'll just put a link here, because this tells a lot about phase distortion, how much it can affect an audio signal. I thought it was really cool. You look at the examples on there. So actually, the effect of a phase change, phase distortion, can be very significant. But the amplitudes don't change. Okay. So you have here continuous time, discrete time. We talked about the signals, systems. If you have, so far we said, if you have a system with impulse response h of t, and the input is x of t, the output is y of t. The output is going to be x of t convolved with h of t. Now, if you look at the same system in the Fourier domain, same system is h of f here. Look at the Fourier transform. The input we look at is not f, omega, right? We always use omega in this class. In my communications class, we use f, but it doesn't really matter. The formulas are slightly different. That's all. Y of omega is the output. Now, your y of omega is going to be your h of omega multiplied by your x of omega, right? Multiplication. And of course, in discrete time, we have e to the j omega. Okay, so the magnitudes are multiplied. Now, in this case, if you took the absolute value of both sides, you would see that nothing changed. Right, so multiplication goes like this. But remember, y of omega is equal to absolute value of y of omega times e to the j times some angle, right? That's introduced by this, right? Because it's a complex number. So it has a magnitude in the phase. And the same is true, of course, for h of omega. And x of omega. Okay, so let's write this equation again in terms of magnitude and phase. So magnitude of y of omega, e to the j angle y of omega is equal to magnitude of h of omega times that angle multiplied by x of omega. Right, now a couple of things. I'll switch these two together. And I already know y of omega is actually equal to h of omega times x of omega. Right? Here I have an angle h of y of omega. And here I'm multiplying two exponentials. Remember, like e to the a multiplied by e to the b is equal to e to the a plus b. Right? So you have e to the j angle of omega, h of omega, plus angle of x of omega. So now that's where I get this, the fact that this is true, but also the fact that the angle of y of omega is equal to the angle of h of omega plus the angle of x of omega. And this applies to both discrete time and continuous time signals. You can do the whole proof again for continuous discrete time signals, you get the same result. No different. So the phase are added, and your magnitude 1 and the angle is negative omega t0. If you have this system, which is a first order system, the magnitude is always 1, right? Only an angle part, and the angle is negative omega t0. If a signal is applied to a unity game system with nonlinear phase, the complex exponential components will be shifted differently, and the resultant signal will look different than the input signal and will sound different. Input signal, you can look at that page that I linked to for the sound change, when you change the frequencies, when you change the phases of the different frequencies, not the amplitudes. So phase delay gives time delay in seconds, which is, we did this, yeah, we did group delay, phase delay, phase linearity. Yeah, I mean, okay, log magnitude and phase plots. So log plots are known as Bode plots. So this part we did not do, pretty sure. I didn't talk about Bode plots because this is a kind of a new topic. And we use Bode plots a lot in circuits classes, but also in yeah, in characterizing circuits, I think that's the biggest thing. But it's part of control theory as well. So for any kind of system that you do, the Bode plot shows you the magnitude on one plot and the phase on the other, okay, of any signal or system. Generally, we look at systems this way, okay? So on the x-axis, we have frequency, and on the y-axis, we have magnitude in decibels. Now, first of all, what is a decibel? Okay, this comes from Bell Labs, which was a big research lab in the US. And they did a lot of the first research in communications in many areas. So that's where it comes from. And the idea here was that instead of looking at just the magnitude, so often they were looking at y of omega divided by x of omega, which, as we know, is h of omega for different circuits. And when you look at these, you're often interested in both the when this is a large number, or like a 1, like a constant number, when the signal is going through very well. But sometimes you want to also look very carefully at the places where maybe there's not a lot of magnitude, right? You're not passing the signal through at all, right? So if you and that changes with frequency. So at a specific frequency, right? If your input and output are the same, system is passing it, then you should see h of omega, the magnitude of h of omega, equal to 1, right? Maybe for some frequencies, omega, it's equal to 1. And then after a while, because of the way systems work, there's usually a bandwidth. So what will happen is less and less of the output will go, input will go to the output. It will be decreasing. So like you'll still be giving the same amount of input, but the magnitude of your output will be like 0.2. Okay, so this happens on purpose. Sometimes we do this, for instance, to remove hissing noise in any kind of audio recording, right? The hissing noise is generally very high frequency noise for large omegas. I want to make that go away. I can use what's called a low pass filter. I'll pass all the speech or music, but the hissing sound will be multiplied by, like, will not go through into the system. I won't be able to hear it, and that's a good thing, right? And sometimes it's not on purpose. For instance, if you have a communication system, okay, I think you guys are gonna eat that. So yeah, if you have a I'll wrap it up now. If you have a communication system and there's a channel, wireless channel, or just a wire channel, like a cable coming into your system, sometimes some frequencies the system works really well, and other frequencies the signal just can't get past. So yeah, so in that case, that's kind of a system that you don't want, but it happens anyway. So you want to see both ends on the same scale. So the decibel is when you take this y of omega divided by x of omega, and it's not for the phase, this is for the frequency. You take the absolute value, and then you take the log base 10 of this, and then you multiply it by 20. Why by 20? They made it up. There's no reason for this whatsoever. Okay, so this is the value of y of omega divided by x of omega in dB. Okay, so lots of things are measured in decibels. For instance, sound is often measured in decibels. If you have a sound meter, you'll see it in dB. In the input-output stuff for circuits is measured in decibels. For all communication systems, usually use decibels. So it's like you will more likely to see decibels in any spec sheet than you are to see absolute value. Okay, so know that means that this equation is happening. Instead of just giving you this value, they're giving you 10 log 10 of this value. Now the logarithm, what that does is for small numbers, it makes the distances larger, so you can differentiate between the distance between 0.001 and 0.01 is the same as the distance between 0.01 and 0.1 or 0.1 and 1 when you take the logarithm, right? Because the logarithm of this is 0, the log base 10 of this is -1, log base 10 of this is -2, log base 10 of this is -3. If you multiply by 20, this becomes 0, this becomes -20, this becomes minus 40, right? And this becomes -60 in dB. So 0 dB means that the input magnitude is equal to the output magnitude. The system is just passing the signal through. But any of these EBs means that it's decreasing the magnitude of the signal and going down by 20 dB. In fact, for 0.5, the value is minus 3 dB, and we consider this to be a very important number when the, actually that's not true, it's for 0.5 square root of 0.5. It's in minus 3 dB. Okay. Now we're looking at this when it's y is in volts and x is in volts. Then dB is 20 log 10 of y divided by x. Usually y is output, x is input. I'm just wrapping up. Okay. But if y is in watts or joules, and x is in watts or joules. In fact, let's not put y and x, let's put the squares, right? Because the square, v squared and I squared give you power. So in that case, when you calculate dB, then you use 10 log 10 because you have the absolute value of y squared divided by the absolute value of x squared. Okay, so I'll wrap it up now. And you guys, I'll see you next week. Take care of yourselves, and we'll talk again. We'll have another discussion in class. Maybe we can have a better time for that extra class again. Okay. Okay. Any questions? There's only 4 people here now. Any questions? Okay. I'm off. Take care.